Today is going to be lecture 2, and it's going to be the first kind of mathy lecture compared to the first one, which is just kind of introductions and how's everybody doing. So we're going to be talking, well, maybe I'll start before we get into what we're going to be discussing today. I'll start with kind of another one of those mental exercises, like the what is space exercise from lecture 1. But before we dive in, is there anything that anybody wants to discuss? Any questions from last time, or just questions in general, or is it time to start talking about space? Give you all a couple seconds to think about it. All right, let's do this thing. So I'm going to stop my video, and I'm going to move y'all. So I have 2 monitors now. We're going to see if should be able to monitor the chat. Okay, there you go. So hopefully I can keep a better eye on like if somebody has their hand raised, but still I can't promise it. So the best way to get my attention is to definitely speak up. I'm going to share my screen. Just going to share my whole screen 1, and I'm going to open up the PowerPoint presentation and move you all over here. All right, let's see. Do you see the orange thing at the top of the screen here where it says you were sharing the screen, or is that only on mine? Just wondering.
And that's only on yours.
Okay, good. See, that's what I thought. That's how I thought the other one worked. All right. So before, I think this is a good idea to come back to the course map whenever we have a moment. So this is the beautifully drawn PowerPoint art depiction of mine of the entire course. And everything is on here, even all the way down to the turtles. And so what we're going to be talking about today, and for the first decent chunk of the course, is a review of orbital mechanics and like the tools that we will need to describe the state of the vehicle and to propagate the state of the vehicle. So if I say, what is the state of the vehicle? First of all, what does that even mean? And then what does that mean in reference to, and so on and so forth. And later we'll get into really fancy stuff like star-based navigation and planetary navigation and Kalman filtering and all that. But we have to start with the foundation, the basics, and that's going to be orbital mechanics. So that's what we're going to start with today. And so actually, I had a really good discussion at the end of last lecture, right before I signed off. Jonathan, are you here today? John DeLuca? I wonder if I can ask you a quick question. I was going to do a reenactment of our discussion after lecture last time.
Sure.
All right, here you go. So I'm going to put you on the spot, so I hope you were paying attention. All right, so let me start drawing here. Get the whiteboard going. There we go. And let's see. So let's say that we have spacecraft. Hang on, is my OneNote misbehaving? There, bear with me. Oh, you know what just occurred to me? My OneNote might give me, all right, here. Let's see here. Is this? Oh, nice. Okay, new strategy. Sorry, I'm having some technical difficulties on my end. Just give me 1 second to get this sorted out. All right. The issue comes from the second monitor. Okay. So temporarily, I'm just going to go back to having only 1 monitor. It's just, it has to do with the pen tablet that I'm using. It's you don't need to concern yourself with it, but just trying to make sure that I can actually like write on the OneNote. So everybody can still hear me, hopefully, no issues, no hiccups.
It's good.
Good. All right. Thank you for bearing with. This should go a little bit more smoothly now. So let's say that you have a spacecraft, and this is going to be my depiction of a spacecraft. I like the Apollo Command and Service Module because it's just a rectangle and then 2 triangles. So you've got spacecraft and there's people on board. So Jonathan, you're on the hook. Where is this spacecraft? Do you remember what you said to me?
In reference to what?
In reference to what? Exactly. That's exactly the right question to ask. And that might be kind of a clue because our lecture is called Reference Frames and Epochs. So we're going to be discussing that. So you've got a spacecraft. I want to know its position. Okay, let's say I give you an answer, John. So you're still on the hook. You're not done yet. Let's say I want the position relative to the Earth. So here's the Earth. We got some continents, right, and some other stuff, and maybe Antarctica down here. Great. What is the position of the spacecraft now?
You said in reference to the Earth?
Yeah, in reference to the Earth. So it's probably going to be the vector from the center of the Earth to the spacecraft, right?
Yes.
Okay, cool. Hopefully we all agree. We're going to call that R. That's probably going to be the letter that we use the most in this class. R for position and V for velocity. Why not P for position? That's a great question. That just seems to be the way we do things. I think R is like the radius, basically, like the radius from the center of the Earth. So we're going to use R for position. Great. So let me ask you then, what is R equal to? Right, so it's going to be, it's a vector, right? So it's got some vector components. It's got an X, a Y, and a Z. All right. Next step, John, you're still on the hook. How do we answer this?
We need to form a set of bases
Yes,
on the
exactly.
Earth.
Very good. Very good. So what you've just intuited and what hopefully other folks could follow is we need a set of basis directions. So let's say that this is X, this is Y, and this is Z. Now we could, in theory, answer that question, right? It's an answerable question now. But the first step was defining the reference frame. So I think that is really what we're trying to accomplish here today. So thank you, Jonathan. I appreciate you being a willing guinea pig, and I hope I didn't stress you out too much with that. So then somebody else who's feeling particularly brave. Let's see. I'll take a volunteer, or we can do the dice rolling method. So if you're feeling brave, just key in. I'm going to ask you another question.
I'll answer a question.
All right, let's try this, Italia. So we've got a Earth reference frame here, right?
Mm-hmm.
Okay. And remember, I'm not trying to make a fool of you. I'm asking intentionally difficult questions to see what you think.
Okay.
What's the Z axis in the Earth reference frame?
Hmm. Would it have anything to do with like right ascension or anything like that?
Oh, you got one of the buzzwords. Okay. So you're in the right direction. Um, the short answer is like we are defining the Earth reference frame right now. Like so you can pick like what would you make the Z axis of the
Oh,
Earth frame?
I would just make it like the like radius of the Earth plus like basically like I don't want to say the height, but like
Yeah, well,
um
don't worry so much about distances as much as directions, right? So we're talking
okay.
about a direction from the center of the Earth. So you can pick any direction you like. I'm not trying to put you on the spot. What I'm trying to do is illustrate that it's actually pretty hard to pick a set of basis directions because it's like, well, which one's the z-axis? Like, I don't know. You tell me. It's like, well, we need to pick a z-axis and we need to pick an x-axis. We actually don't need to pick the y-axis. We can let that be defined by the other two because right in a right-handed system, x cross y is z and z cross x is y and y cross z is x. So there's really only two directions we need to pick, but it can be pretty tricky to decide what you want those directions to be. And so just really quick, so just throw anything out there. What direction would you pick for the z-axis?
Uh, hmm. Could I just say that it's like the direction of like the poles?
I like that a lot actually. Let's make the z-axis coming from the center of the Earth and going out through Santa's workshop through the North Pole. Okay, there's the z-axis. And the y-axis is done for us. We just need to pick the x-axis now. And this is actually going to be really
Okay.
tricky. It's gonna be
Could
really
we
tricky.
could we say the x-axis is like with respect to the equator?
Okay, so the x and y axis, they would both be coming from the center of the Earth out through the equator because they need to be perpendicular to the z-axis.
Yeah.
So then the question is, well, okay, but coming out of the equator where, right? Because there's an infinite number of directions that come out of the equator. So
Yeah.
we gotta pick one of those.
We could just make it up. We could just say uh the x-axis is like I don't know, uh Johnson Space Center or something.
That's good. That would be great if the people who made the decision were at Johnson Space Center. The people who made the decision, you're shockingly close to the right answer, though. I'm really impressed.
Oh.
The people who made the decision lived in Greenwich, England. You might have heard the word
Oh
Greenwich many
yeah, yeah.
times. Yep. And that's where we get the
The
prime
prime
meridian.
meridian.
Exactly. So that reference system that you just described, which we're going to be talking about in a minute, is called the Earth-centered, Earth-fixed reference frame, which is great. And you don't have to write that down because we're going to talk about it. The problem is that reference frame moves because that's fixed in the Earth, right? And the Earth is rotating, and that's a bit of a problem. So then it's like, well, how do we define a reference system that doesn't move, but it's based on things that are in space, and everything in space is moving? So that's,
Um,
I want to kind of create that sense of like, how the heck do we solve this problem before we start talking about it? Because I think, motivating what we're talking about today is important. But great job, Italia. That's above and beyond what I was expecting. So excellent.
Thanks.
Okay, so I'm going to start writing out the notes now. This is where it gets a little bit boring. I'm trying to decide between typing them out and handwriting them out. I'm going to really work on my handwriting and we're going to try our best. So everybody just bear with me for a little bit. So, navigation means determining your state. And that would be position, velocity, and attitude, given available measurements of your surroundings. All right, so vibe check. Is that legible enough handwriting, or do you all want me to switch to typing?
It's good.
Good enough? All right, that's I'm doing my best. We'll see if we can improve on that. So here comes the first dad joke of the class. Unlike a spacecraft, a state cannot exist in a vacuum. That's a fun little pun. So the question, whenever you're talking about a state, is in reference to what? That's the question we're always trying to answer. So position relative to what? Velocity relative to what? So on and so forth, right? It's going how fast? Well, it's going this fast compared to the Earth. It's like, well, how fast is the Earth going? Well, it's going this fast compared to the sun, and so on and so on and so forth. Everything in space, there are no fixed points. Everything's moving, and everything's moving with respect to something else. So we need some well-defined reference frames in place before we can ever start assigning numbers to position and velocity and attitude. So on the surface of the Earth, let's talk about degrees of freedom for a moment. On Earth, we have position, and you can think of that in terms of latitude and longitude. That's 2 degrees of freedom, right? We would agree that position is a 2-degree of freedom problem. I should mention this is degrees of freedom. That's what I mean by DOF, degrees of freedom. So you can move in the latitude direction, you can move in the longitude direction, right? You also have speed, which if this were a nautical vessel, we might measure in knots, miles per hour, etc. That's 1 degree of freedom. And then you also have heading, which would be maybe degrees, if you're reading off a compass, degrees with respect to north would typically be how we would describe heading, which is 1 degree of freedom. So hopefully people are convinced that on the surface of the Earth, if you know 4 numbers, you know your state. You know where you are, you know how fast you're going, and you know where you're going. In space, it's different. and this might be obvious, but we have to talk about it. In space, we have position, which would be X, Y, and Z with respect to something. So immediately we have a 3 degree of freedom position problem. You also have velocity. Notice speed is a scalar, velocity is a vector. Velocity, you can think of X dot, Y dot, Z dot, also 3 degrees of freedom. And then does somebody want to hazard a guess? Instead of heading, we have what we call attitude. How many degrees of freedom is attitude? Taking any answers.
I think it's 3.
3, good, but that's not enough of a right answer. Tell me more. 3, how would you describe your 3 degrees of freedom of attitude?
Sort of spherical coordinates, but
Spherical
without
coordinates?
any length.
Yeah, you could do something like that. There's actually, what we're going to talk about in a couple of lectures is there are many ways to describe your orientation. I'm going to go with something really simple right now from aircraft stuff. You might have heard of your roll, pitch, and your yaw. Those sound familiar?
Yeah.
I hope so. That's also 3 degrees of freedom. So one way to describe your attitude is with a roll angle, a pitch angle, and a yaw angle. There are other ways of solving it. But so in space, your full state has 9 degrees of freedom. So you're not done until you've answered all 9 of these things. Whereas on the surface of the Earth, it's 4 degrees of freedom. So it's a little bit of a harder problem. Now, in reference to what is really the key question of today, a reference frame requires a reference point or an origin and basis directions. We already went through the exercise of talking about that with Jonathan and with Italia. So great job on that. So let's say for a minute, here comes another diagram, and y'all are going to start wincing before I start drawing these diagrams here. Let's say that you've got sun, and the sun has some reference frame. And you've got, those are the rays coming off the sun. This is how you know when I'm drawing stuff. I guess I could do different colors. The sun has rays coming off of it. The earth has little continents. So it's like, you got like that shape. There's the earth. The earth has its reference frame. So you've got the earth with respect to the sun. And then you've got the moon. And the moon has its reference frame. Those might be aligned, they might not be aligned. And then let's say you've also got a spacecraft, which is going from the Earth to the moon, and it's just a little box with 2 solar panels. And then it's got its reference frame. And then hanging out the side of the spacecraft is a camera, which has its reference frame. So you've got a camera reference frame, a spacecraft reference frame, a moon reference frame, an Earth reference frame, a sun reference frame. And we need to keep track of all of these. And then actually, to make it worse, the Earth has 2 reference frames and the moon has 2 reference frames. And so we get to play a game that I like to call, whose frame is it anyway? So that's what we're going to be discussing today. So hopefully by the end of today's lecture, the different reference frames, first of all, the necessity of reference frame should also already be pretty straightforward. We need to understand why we need these and then also how they're defined and what are the common reference frames. So it's not obvious. It's not obvious. What directions we ought to use when forming a reference frame. And I've already said this, I'm just kind of writing it so it's in the notes. There are no fixed points. Or directions in space. So instead, what we do, we define a direction as it was at some particular point in time. What we call an epoch. So therefore, a discussion of celestial reference frames would be incomplete without some discussion of time and timekeeping. There we go. So, a lot of words. Today's going to be a bit of a wordier lecture than some of the other ones. As a matter of fact, I'm looking at my next page of notes and it's all words. So just have to bear with me for a little bit. Questions up to this point? Everybody content? Feeling good? So, a brief history of time. And yeah, that's a play on the Stephen Hawking book, Brief History of Time. So here's a fun exercise. I'll take another brave volunteer who hasn't gone yet today, or we can do the dice rolling method. Who wants to answer some questions about time?
I can go.
Want to try it? All right.
Sure.
So let's see. What is the most basic unit of timekeeping that you can think of? This is not I want the textbook answer. I want the answer that makes sense to you.
A second.
A second. Okay. How is a second defined?
We did something with cesium atoms, I think.
Oh, bleh. Okay, that's where I'm going. So pretend you don't know that. Okay, so you knew the answer. You're right. We did something with cesium atoms is the right answer. What I was going to say, pretend for a moment that the second is not the basis of all modern timekeeping, which it is. Now answer the question. What's the most basic unit of time you can think of?
Probably a day.
Probably a day. Exactly. Very good. What is a day?
I mean, if I had to define it, I'd put like a little stick in the ground and draw a line and do a little sundial
Yep.
and then tell you it's been a day when the
it's
stick lines back up with the shadow.
exactly. Yep. No, that's exactly it. So you could define a day as the length of time from apparent solar noon to apparent solar noon. That's the
Yeah.
that's the sciencey version. I bet you literally nailed it. You actually nailed it twice because first you gave me the modern answer, and then when I asked for the ancient answer, you gave me that one too. So fantastic job. All right, so here comes some writing. So just bear with me here. So the most basic, and if anybody gets to the point where they just can't handle my handwriting anymore, we can switch to typing, but this seems to be okay. Because I think me actually writing it out paces me, so I don't like talk faster than y'all can write. The most basic unit of timekeeping is the day. Defined as the time from apparent solar noon to apparent solar noon. Right? So then people said, all right, we need lengths of time that are less than a day. So we came up with something called hours. And seasonal hours are divide, it says divide the period of sunlight into 12 equal sections and divide the period of night into 12 equal sections, which you might notice change in time because every day is a slightly different length than the day before and the day after, because of the precession of the Earth and the motion of the cosmos and everything. You have longer days in the summer and shorter days in the winter. So this method is fine if your whole society runs on farming, but after a while, you start to want something that's a little bit more precise. So after a while, we came up with a word that I've only read and never pronounced, so wish me luck. Equinoctial hours are divide a day into 24 equal sections. And that's what we have today, equinoctial hours. And so we have 24 hours in a day. And then finally, somebody said, okay, we need something even better than that. So we can divide equinoctial hours into degrees of minuteness. Minute meaning small. And those are minutes. And we can say, hey, that was fun. Let's do it again. Let's divide minutes into a second degree of minuteness. And those are seconds. And I did not make that up. And I'm sure at least one of you, your mind are blown because that's where those words come from. But yep. So the first degree of minuteness gives us seconds, and then the second degree of, well, the first degree of minuteness gives us minutes, the second degree gives us seconds. And for most of history, seconds were a completely academic construct, right? If you were working as a farmer, which is what most people did forever, then seconds would be completely useless to you, probably as would minutes. Hours kind of matter because how many hours of sunlight there are left in the day. People would look at seconds in ancient times the way we might look at nanoseconds now. It's like, yeah, okay, science nerds care about that, but I don't care about that. But the thing is that in this class, we are the science nerds, and we will find that nanoseconds absolutely matter when it comes to space navigation. So actually, it was, here's a fun question for anybody who's going to shout out the answer. When was it that society was forced to start synchronizing our clocks like wide scale? What prompted that?
Oh, I think I know the answer. Was it when we started using trains?
Exactly. That is
And
exactly right.
like especially when we got the like trans continental railroad, and that's what like prompted people to get different time zones.
Exactly. Yeah, because what used to happen was there would be one big clock in the center of town that some science nerd would make sure was lined up properly, but then each town would have its own different time. And it wouldn't matter if you were riding on horseback between towns, but if the train from Chicago needs to arrive at 3:45, we all need to agree what 3:45 is. So railroads are what forced us to synchronize our clocks. All of a sudden, minutes matter. But then radar and light-based communication, which is what we have now, so with railroads, minutes matter all of a sudden. With radar and light-based communication, nanoseconds matter. Very good. All right, so that's quick discussion of time. Might seem like a bit of a tangent, but we're going to get into the first official way of defining time, kind of the way that it is now, which is called atomic time. And Abby already grabbed this one from me. So it used to be that 1 second is 1/60th of 1/60th of 1/24th of 1 day. But that is not good enough. let's call that precise, for extremely high precision applications. Okay. So you could also say that 1 day is the time from the apparent local noon to apparent local noon is also not good enough, right? So what we said is the new base unit of time is the SI second, which is defined so that it can be easily measured by atomic clocks. That's a K. Yes, okay, cool. So atomic clocks, just a quick aside, I'm not an atomic clock expert, so this is the beginning and end of my knowledge of them, but atomic clocks count cycles of a high frequency electrical signal that is kept in resonance with an atomic transition. I'm going to start to scroll down a little bit here. So the new definition of an SI second, SI second, and we're going to use that symbol that we saw on the first day, is defined as, which is the equal sign with the little fun hat on it, is 9,192,631,770 periods of oscillation of radiation. Oh, sorry, not periods of oscillation. Whoops. Forgive me. There's my first typo. Periods of radiation. Corresponding to the transition between two hyperfine levels. Isn't this fun? This is going to get interesting soon, I promise. Of the ground state of the cesium 133 atom. There you go. So that's what Abby already had. We did some stuff with cesium, and someone who is an expert in atomic clocks, which is not me, decided that if you look at cesium and it oscillates 9,192,631,770 times, that's a pretty good second. And so we define seconds that way, and all of a sudden we can start working backwards. We can say, okay, if a second is this long, then we know exactly how long an hour is, and we know exactly how long a minute is, and we know exactly how long a day is. And we can actually start to notice that the Earth's rotation itself is not as consistent as we thought it was. We start learning all sorts of neat stuff about the Earth. So the time system based on this new unit is International Atomic Time, which is abbreviated as TAI because it's French, so it's backwards. So TAI, which was introduced in January 1972, is now the basis of all other time systems. It's the basis for interpolation and prediction of all other time systems. Now, the implication here is that you don't need TAI to get to the moon because this happened after the moon landing. But it's definitely very, very useful for our modern applications. And we will see, especially when we get to GPS measurements and stuff like that, that nanoseconds do truly matter. And that's something that we're going to want to keep track of. So, questions on this? Doing okay so far? I know this is not talking about space. Today is going to be a little bit more boring in that respect, but it will get interesting again soon. I'm going to move on, unless somebody wants to chime in with a question, to talking about what's called sidereal time and solar time. So, first of all, it helps us to know this. Days fluctuate in length due to changes, we'll say perturbations, that's the fancy word, perturbations in Earth's rotation. So remember that a solar day, per Abby's definition, is apparent local noon, or apparent solar noon, to apparent local noon. And that's 24 hours. On average, right? Okay, so somebody else who isn't Abby and who hasn't answered me yet today, looking for a brave volunteer to talk about the rotation of the Earth. If it's somebody who's taken Kurt Anderson's spaceflight mechanics, you're going to be in a great position to answer this question. Got a volunteer?
I can go, Paul.
Want to try it? Okay, let's see what we can do. How long does it take the Earth to rotate about its axis once?
Well, around the Earth's axis is just over 24 hours. So about 24 and a quarter hours, but not
It's di-
exact.
Is it different? So it's not, why wouldn't it be 24 hours?
Just wasn't divided into 24 hours,
It
different
wasn't divided.
days.
So there's an idea, and actually what I'm going to do is, so here, I think you basically have the right answer. I'm going to define what's called a sidereal day. I mean, I'm not defining it, but that's what it is. Which is a 360-degree spin of the Earth about its axis. And this is not 24 hours. And this comes as a big shock to a lot of people. It's like, why wouldn't that be 24 hours? So here comes a diagram, which to me, everything clicked when somebody did this. So you've got the sun. Remember, that's our code for the sun, is when the rays are coming off of it. And let's say that you've got the Earth. And let's say that you've got observer on the Earth, right? And the Earth is doing its thing. It's orbiting and it's rotating. So remember, it is spinning this way, but it's also spinning, you know, it's rotating and translating as it orbits. So sometime later, and we'll say actually almost 24 hours later, it's over here now. And it has spun once about its axis. And then sometime even a little bit later, it is now pointed directly at the sun again. So what we see is that the length of time it takes to point at the sun twice is not the length of time it takes to spin on its axis twice. So this right here is a sidereal day, and this is a solar day. And they are not the same thing. Not the same thing. Actually, if you'd like the Snapple fact, a sidereal day is just a tiny bit less. I think you just had it backwards, Kevin. 23 hours, 56 minutes, and 4 seconds approximately. So you figure it just takes you that much longer. It takes you 3 minutes and what is that, 56 seconds longer to crane around and point at the sun again, because this is a grossly exaggerated diagram, right? But you get the idea. So your sidereal day and your solar day are not the same thing. And as a matter of fact, I can scroll down here. There we go. A sidereal day is measured with respect to the stars. Which would make sense, right? Because compared to the sun, the stars are basically standing still. Really, the stars aren't standing still, but compared to the sun, they are, right? That's kind of the idea. So to deal with, this is a bit of a separate discussion, but to deal with perturbations in the length of a day, in 1895, a fictitious mean sun, not like it's rude to people, but like on average, was proposed to account for fluctuations. So as early as 1895, people knew that regular just solar noon to solar noon probably wasn't going to cut it, for fluctuations in the length of a day. And then this became the basis for what we call mean solar time. Kind of sounds like it could be a band name. And so from there, I'm going to scroll past my diagram here unless anybody wants me to go back to it. That leads us to a discussion of universal time and leap seconds. All right, so let me just skip ahead. We're at about the halfway point of the lecture, so I'd love to take a break, but at the same time, we're just a little bit shy of halfway through my notes. So I think I might try to keep on chugging. I hope that's all right with everybody. I'm going to try to speed up a little bit next time here. So mean solar time as it is experienced in Greenwich, England, Greenwich, England, because when people started making these definitions, London was kind of the capital of the world, basically, right? And Greenwich is right outside of London. Nowadays, you know, we might put this at Johnson Space Center or wherever else, right? But back in the day, mean solar time in Greenwich, England is defined as universal time. So those of you that have served in the armed forces might have heard of like Zulu time, right? This is the time with respect to like everything else, right? You got your actually when you're setting up your computer and you say Eastern time, it'll say in parentheses UTC -5. Now we're getting somewhere. That's universal time, right? Now we should mention here that before you get to universal time, there's one more step. Oops. Hang on. There we go. Sorry, I got some stray marks here. There's one more step before we get to UTC. So you must further correct to account for Earth's polar motion, right? The precession of the poles. So then we have something called coordinated universal time. So we got mean solar time, universal time, coordinated universal time, international atomic time. If I was giving out quizzes, I would like make you study all these on a flashcard, but it really doesn't have that much bearing into our navigation stuff we're going to do later. It's just important to know the history here. Coordinated universal time, which is UTC because it's a French acronym, is a correction of international atomic time, which remember is TAI, by an integer number of what we call leap seconds. So you've heard of leap years and leap days. Now get ready for leap seconds, such that it matches universal time. I'm going to scroll down here, bear with me. Sorry. UTC is a correction of TAI by an integer number of leap seconds such that it matches universal time to within 0.9 seconds. Oh, there we go. My OneNote's getting a bit freezy right now. Leap seconds are added at the end of June or December as needed by the Time Council. I'm just kidding, that doesn't exist, but there's probably a group of people out there that are in charge of this. To date, 37 leap seconds have been added so far. Actually, might be more than that. This is last time I took these notes was 2018, so there might be 38 leap seconds actually. So actually, I'm going to say check me on this. And so then I would say UTC is what I was alluding to earlier, is the standard by which the whole world calibrates its time. Or I should say calibrates its clocks today. So I refer to it as internet time. Because you know that your phone, the clock on your phone is more accurate than the clock in your car, even though one of them isn't necessarily fancier than the other. The clock on your phone has the internet, and so it checks the internet to see what time it is, right? Oh, Italia said it's still 37 seconds. I appreciate you. Thank you. So UTC is the standard by which the world calibrates its clocks today. So when you're playing around with your laptop and you're saying that you live in the Eastern time zone, it'll say UTC -5. That's basically the idea. Okay. So we're almost done talking about time. We've got 2 more bullet points on time, and then we're going back to reference frames. Those of you that are familiar with something called SPICE, which we will talk about, users of the SPICE ephemeris system for keeping track of the position, velocity, and attitude of planets and spacecraft, developed by JPL. That's a capital P. Developed by JPL, will be familiar with leap seconds, and you will all be familiar with leap seconds at some point. Because SPICE requires the user to have what we call a leap second kernel, or LSK files, to determine the state of a planet, asteroid, moon, spacecraft, etc. There's a C in there. So when we get to homework 1, you will need a leap second kernel file, and I'll explain how to get those. That's not too complicated, but it's just so now you know what that means. It's like, oh, this is to keep track of exactly what time it is as we propagate time into the future, that sort of thing. Okay, questions about time. Otherwise, we're going to get back to reference systems and reference frames. So far, so good? All right, sounds good. So now we're on to reference systems and reference frames. Okay. So a reference frame, oh, I'm sorry, yes, reference frame consists of, we knew this already, a point, a reference point, what we might call the origin, and a set of basis vectors and those basis vectors are typically what we would say mutually orthogonal. Orthogonal. Actually, I'm getting ahead of myself. They're not just orthogonal, they're mutually orthogonal. Here, bear with me. Trying to select the eraser button here. All right, let's do this. Oh, good. Sorry, OneNote's wigging out on me here. Trying to just erase this, and I appear to have frozen it altogether. But the idea behind mutually orthogonal is to say that x cross y is z, z cross x is y, y cross z is x, right? That sort of thing. So these are typically mutually orthogonal. Right. And so then what's the difference? Oh, still drawn. Between a reference frame and a reference system. You might hear those terms used. A reference system is a set of instructions that are used to form a reference frame. So it defines the origin. It defines basis vectors, and algorithms to compute those. There we go. So that means that a reference frame is a realization of a reference system. There we go. And so that leads us to the first reference system that we're going to be spending a lot of time on, which is the International Celestial Reference System, or ICRS. This is big. So this was developed by the International Astronautical, Astronautical Union, or the IAU, from 1997, 2006. Oops. Hang on. I should really know better than clicking the erase button at this point, because that's going to crash it. I found myself wondering how exactly it took them 6 years to come up with a reference frame, and then you think about just exactly how long it takes to be. There's an incredible amount of precision that's involved. So this is from 1997 to 2006. There we go. So the origin is not actually at the sun. The origin is placed at what we call the solar system barycenter. Oh, okay. Barycenter, what we might call the SSB, which is really the solar system center of mass. Not exactly the sun. So anybody who might have this Snapple fact memorized, what percentage of the mass of the solar system is the mass of the sun, roughly? Like how much of the solar system is sun by weight?
Wasn't it like 99%?
Yep, it's about 99%. Very good. So you can imagine that the center of the sun and the solar system barycenter are very close to one another. The solar system barycenter is going to be inside the sun. But it's not exactly the same thing. Technically, all the planets are tugging on the sun, and the sun wiggles a little bit with respect to each of those, and so on and so forth. But yeah, when you see solar system barycenter, it's not the same thing as the center of the sun, but it's going to be mighty similar. So then the axes, the basis vectors, are defined with respect to, oh, I lost my place on my notes here. With respect to, or we'll just say using directions to distant objects. Typically, this is going to sound sci-fi, extragalactic radio sources, such as quasars. Anybody who knows their way around astronomy, what is a quasar? It sounds cool.
Isn't a quasar pretty sure a quasar is a neutron star, but it's spinning rapidly around its axis?
Ooh, so you got the other one. You got a pulsar.
Oh,
So
pulsar.
we're going to be talking about pulsar-based navigation later, actually, which is fun. Quasar. So you get credit for that anyway. A
Thank you.
quasar is the super hot accretion disk around a supermassive black hole at the center of another galaxy. So you can imagine that in a galaxy, as you get closer and closer to the center of the galaxy, things are moving faster and faster. And as you get very close to the supermassive black hole, things go bananas, which is the technical term. And when things are going bananas, they get very hot and very bright. And that's what you call a quasar. A quasar actually comes from the term quasi-stellar object. It's kind of quasar, quasi-star. So it's not a star, but to the untrained observer, it kind of looks like a star, but it's actually another galaxy. So you can imagine that other galaxies are moving pretty dang slow compared to us in terms of the amount of sky that they trace out with respect to time. Those are going to look pretty constant. Really, nothing is constant. Everything's moving with respect to something else, but quasars are the closest things to fixed points that we've got, so we use those to define our directions. So Italia already got one of them. So the z-axis is parallel. Okay. Boy, if OneNote keeps freezing, I'm going to have to keep coming up with more stuff to pad for time. There we go. The z-axis is parallel to Earth's, oh, this is starting to annoy me. There we go. To Earth's spin axis. So that is basically perpendicular to the equatorial plane. Wow. There we go. So the z-axis is parallel to the Earth's spin axis. It's perpendicular to the equatorial plane. Now here comes the hardest part, the very hardest part. because what Italia came up with earlier was the x-axis of the Earth frame. Does anybody want to hazard a guess? And I'll take any answer. And if you know the right answer, I'll be very impressed. What is the x-axis of the International Celestial Reference Frame, which by definition can have nothing to do with the Earth's surface?
Sorry, 1 second. Longitude of 0 degrees on January 1st of 2000, correct?
That is so close. I'm very impressed. I was very impressed. It's not exactly a longitude of 0. Actually, you know what? It might be. I actually don't know if they were lined up. You got the January 1st, 2000 part. So what it is, and get ready for this. It's the ascending node of the ecliptic plane. Ecliptic plane. That's the plane of the Earth's orbit on the equatorial plane. Okay. What the heck does that mean? Doesn't help at all. So first of all, the plane of Earth's equator and the plane of Earth's orbit are two different planes. Those planes line up in a line, you can imagine, in space. And I'm going to draw a picture of this pretty soon. Actually, you know what? I could even draw a picture of it kind of nowish. So you can imagine that you've got the, we'll get a picture in a second. Just use your imagination for now. The x-axis is the ascending node of the ecliptic plane on the equatorial plane. So imagine the vector from the sun to the Earth at the vernal equinox. So this is AKA the vernal, okay, let's try again. The vernal equinox. Vernal equinox is the spring solstice, not solstice, spring equinox, because I can't call it a solstice if it's not. It's the equinox, right? So that's the March 24th, I think, right? March 21st. At that time, the Earth is at a specific point where its equator, its equatorial plane, and its ecliptic plane are lined up. That's the same time as when we have exactly 12-hour days, right? And at the position where the Earth was when that was the case, on January 1st, 2000, at noon, Greenwich Mean Time, that's where we planted our flag in the ground and said, that's the x-axis. You kind of just had to pick something, basically, right? We just had to pick something. And so that's the x-axis. This is also known as the vernal equinox, or what's also sometimes called the first, oops, hang on, sorry, bear with me here. First point of Aries. And if you're not satisfied with my description this far, that's fine. I'm going to be drawing a picture shortly, so just bear with me. And then the y-axis completes. Ooh, this is starting to get annoying here. Completes the right-handed system. So that is to say that z crossed with x equals y, right? X cross y is z, y cross z is x, z cross x is y. This is the middle thing is a cross, and then the second one is an x, so that's not confusing at all. So as I kind of mentioned before, because these planes are moving, all right. Because these planes are moving, you must choose a period of time, or an exact point in time is called an epoch. You must choose an epoch time in which to realize the frame. And so what we chose is noon at Greenwich, England, on January 1st, 2000. And this exact period of time is referred to as J2000. And so, because that time period is called J2000, the ICRS realized at J2000 is sometimes called the J2000 frame. But we will use ICRF in this class. Hang on. Ooh, doggy. All right. In between lectures 2 and 3, I'm going to have to figure out why OneNote seems to be giving me such a hard time here. If anybody's more familiar with OneNote than I am, I'll certainly take any constructive criticism you might have. Yeah, there it goes again. All right. But we can just discuss this. Basically, the ICRF, yeah, so we will use CRF in this class. And so because of this, the ICRF, International Celestial Reference Frame, the XYZ basis vectors and the position, will be the world frame in this class. We will treat it as inertial, even though it is not. And we will talk about what that means in a minute. So International Celestial Reference Frame, that is the world frame in this class. And so here comes your diagram here. So imagine that you have the Earth, right? And here is the Earth's equator. And here's the Earth's spin axis. And so then imagine that you also have an equatorial plane which surrounds the Earth. And I'm drawing it as an ellipse, but it doesn't have to be an ellipse, right? So this is the equatorial plane. And imagine also that you've got some ecliptic plane, like so. So this is the plane ecliptic plane. The plane in which the Earth orbits and the plane about which the Earth rotates. Those are our two planes. The intersection of the two gives us our x-axis. That's an arrow. And the spin axis gives us our z-axis. And so the intersection of the z-axis with the Earth is Santa's workshop, which is the North Pole. And let's see, z cross x gives us y. There we go. And this is the ICRF. Wow, it's like writing ICRF is what does it, but doing that diagram doesn't do it? I don't understand. There we go. All right, so that is the International Celestial Reference Frame. All right, so sometimes, I should mention this. Bear with us here. So there's other reference frames, and by the end of today, we're going to have talked about 5 or 6 of them, and they should all hopefully make intuitive sense. Before I move on, any questions about the International Celestial Reference Frame? Does anything about this seem kind of weird, apart from like the X direction was chosen arbitrarily, but like we had to choose it arbitrarily? Any burning questions about ICRF? Oh, all right. Sometimes a more local frame is useful for a particular application. For example, it would not make sense to express the position and velocity of an Earth orbiting satellite with respect to the solar system barycenter. Right. So what we can do is a little bit of sleight of hand. And if I'm moving too fast past the diagram, just kind of yell at me and I'll scroll back up. Is we can just take the whole International Celestial Reference System, or I should say the frame, and push it somewhere else, right? So the ICRF basis vectors, good gravy. There. Apologies for OneNote being this sticky. I'll figure out what's going on with it here. The ICRF basis vectors moved to the center of the Earth forms what we call. Yeah, I could switch to typing for a little bit. I'm gonna have to draw a few more pictures here. I wonder if I'm imagining that it takes more data for OneNote to keep track of my pen strokes than it does for like a character that I type. We'll try this for a little bit. So just because I'm almost done with a sentence, forms what we call the geocentric celestial. Ooh. Reference. Frame. Which we will call it, we're going to use a different name. We will call this the Earth-centered inertial frame. Or ECI. All right, that's it. That's all. I'm typing now. I've officially lost patience with this thing. I appreciate y'all putting up with me. So hopefully this makes sense. The ICRF basis vectors move to the center of the Earth, forms what we're going to call the ECI frame, the Earth-centered inertial frame. And then let me just try doing text. How easy is that going to be? What happens if I just type here and start typing? Moved. When I type, do the keystrokes get picked up on the microphone and make a ton of noise? Let me know if it does that. Let's see. Try closing the app and agree. Yeah, I might do that. That might be the move. So can I just do, I guess it saves. Oh boy. It saves as we go, right? Because I'm going to be real miffed if this doesn't save. I think it ought to. Yeah, I think it just saves as you go. Yeah, it'll save. All right. If it doesn't, I'm going to get mad at you. All right. Also, this computer's as old as dirt, so we'll see. I might just need a new computer. All right. There we go. Delete this. Let's see if that behaves a bit better. And I appreciate you all for putting up with me here. So we'll try writing a little bit more. And then if we move to the moon, yes. So the ICRF basis vectors moved to the center of the moon. Well, you can probably guess. We'll call this the moon centered inertial frame, or MCI. All right. Beautiful. So we'll do a quick little diagram here. So now we know of 3 reference frames already, right? So you've got the sun, which, remember, I have my little sun rays coming off of it. And we've got, actually, you know what? Let's erase that for a second. Switching to eraser mode seems to be what does it. It doesn't like that. What I wanted to depict was that the up direction, yeah, come on now. There we go. The up direction is not necessarily the direction. So imagine you've got the sun, you've got the earth, and then you've got the moon. And all of these are aligned with Earth's spin axis. Right? So you've got X, Y, Z, and this is what you might call the ICRF at the sun. Those same basis vectors moved to the Earth is the ECI, and those same basis vectors moved to the moon, it's all the same directions, is the MCI. That's at the moon. So we have a question here. This is a problem, right? Remember that we're treating these as inertial. Seems to be working better. Thank you for the tip. We are treating these frames as inertial. Why is this a problem? That's an open question. First of all, if anybody's feeling brave, what is an inertial frame and why aren't these inertial frames? Anybody?
I can try.
Let's hear it.
Inertial frames are frames that are not accelerating.
Very good. And they're also not, there's one other thing.
Rotating, I
Very good.
suppose.
Yep. So these are not rotating. So these are good, but they are accelerating, as in the reference point that they are centered about is accelerating. It's okay for them to move along a constant velocity, but remember that the moon is spinning around the Earth is spinning around the sun, and then the sun is spinning around our local galactic, our what's it, local stellar neighborhood, right? It's all moving. So what ends up happening is we can treat these things as inertial for sufficiently short periods of time and get away with it, as in like, as long as it takes to get to the moon and back, it's usually good enough. But longer term, we need to be careful. These are not truly inertial frames. Now, here's a question. So I'll have you follow up on that. Why would we care if a frame is inertial? Like, what's the benefit to that? Why not use any old frame you want, like a rotating frame?
Because then we don't have to account for because Newton's laws apply properly, right?
Exactly. It's like you had this memorized before I called in. All right, perfect. So yeah, exactly that. So we're going to talk next about inertial frames and body fixed frames, and that is going to finish us up today. Let's see here. Inertial frames and body fixed frames. So here's what I think I'm going to do. It's going to take me more than 9 minutes to go over this, but probably not more than 20 minutes. So I think I'm just going to keep right on chugging. I'm just going to get through all the material. If you need to leave, you're certainly free to leave at any point you like. I think technically I should be dismissing people kind of nowish, right? Because we're getting close to the 1.5 hour mark. I'm just going to keep going just because we're on a roll and I want to get through this last page of stuff. But if anybody needs to take off, I certainly won't be miffed at you. And you can get caught up from the video later. So, and I promise never to go over 2 hours, but I might need to go slightly over an hour and a half. An inertial frame has non-rotating basis vectors and a non-accelerating reference point, or say non-accelerating origin. An inertial frame is also sometimes known as a Newtonian frame. I think those of you that have taken Dr. Anderson's spaceflight class or any of his dynamics classes will have heard this referred to as a Newtonian frame. Same thing. None of the frames we're discussing today, none of these frames are truly inertial. But we can get away with treating them as inertial. As such, for sufficiently short periods of time. So this is where we come to a quote, which I've heard somewhat recently, which I absolutely love. All models are wrong. Some models are useful. So this is where our engineering comes in. It's like, yeah, well, the center of the Earth is kind of not accelerating really. Over the time span of a couple of days, who cares? Really, it does matter, but we're going to say for now that it doesn't for the sake of our dynamics that we do in this class. All right, so last page of stuff. We may want to use a frame that is fixed, or we say it has axes in a planet's surface. Or a spacecraft body. Or an instrument. Camera. Etc. Part of the reason we might want to do that is for a rigid body, it's an O, the position of each point over time is constant. So now we're going to get back to Italia's frame from the beginning of lecture. So we're going to say, consider a frame at the center of the Earth that we'll define as follows. Its z-axis is the North Pole, which is the same thing as Earth's spin axis. The x-axis, exactly as defined earlier, is the intersection of the equator with the prime meridian. Or you could think of it as 0 degrees latitude, 0 degrees longitude. I'm going to just erase that. I think I'm just going to do LON instead of LONG. Well, when it lets me do that. So that was exactly what we were talking about before, right? You kind of just need to pick a direction for X. It can be somewhat arbitrary. We're going to pick this and then move forward. 0 degrees lat, 0 degrees long seems perfectly reasonable for our x-axis, and then y-axis completes the right-handed system. All right, so this is what we call, and we already alluded to this. Oops, scroll up a little bit. Let's do that. This is the Earth-centered Earth-fixed frame, or what we call ECEF. So that's the frame. If you're describing something on the surface of the Earth, that's great because your position on the surface of the Earth, if you're sitting still, is constant, right? But your position on the surface of the Earth in the ECI frame is always moving because of the rotation of the Earth. So just depending on what we're trying to describe, we might want to use one frame over another frame. What's really nice is the relationship between the ECI frame and the ECEF frame is a simple rotation about Z. Nice and simple. So here comes a diagram. So questions while I'm drawing the diagram, questions about the ECEF frame and the ECI frame. Hopefully those make sense. Oh boy, I can do slightly better than that in terms of a circle. Yeah, man. In a minute. There we go. It seems to like it better if I use my mouse to click that. Anyway, so just to really quickly visualize the difference. That's a better circle at least. So imagine that this is the Earth and that here's the equator and here is the prime meridian and this is the center of the Earth. Then the ECEF frame would be coming out the top. This is the X direction and then the Y direction is going to just complete the right-handed frame. But then we could also say that there is some other frame, and I'll use red for this when it seems to like it. There we go. And there's some other frame where Z is the same way, and it's got some direction here and some direction here, where this is the X frame and this is the Y frame. And we'll say that red is the ECI, and going back to the black frame, that's the ECEF. It kind of matters that I can click back to the black when I want to. Come on, there we go. And that's the EC. And the difference between them is just some angle theta, where theta is 0 all the way up to 2 pi as Earth completes one sidereal day, not one full solar day. Right? That's an important distinction. Okay, so then that's that. There we go. We'll scroll down a little bit. Almost done. I know we're at 7:30, 6:30 for me. One last frame we got to talk about. Consider a frame. You might know where we're going with this already. At the center of the moon. Just shout it out. Anybody want to guess what this frame's called?
Moon-centered, moon-fixed frame.
Yep, that's exactly it. Moon-centered. So the last one was Earth-centered, Earth-fixed. This is going to be moon-centered, moon-fixed. Very good. So Z-axis is out the moon's spin axis, which is the moon's north pole, which is not the same as the Earth's north pole, although they are similar. I almost said the moon's earth pole. Whoops, hang on. Moon's north pole. So if Santa had an auxiliary workshop on the moon, that's where this would be. So moon's north pole. The x-axis is, again, 0 degrees latitude and 0 degrees longitude. But then that begs the question, what the heck is that on the moon? How do we define latitude and longitude on the moon? So what this is the point on average, which is directly facing the Earth. So the point, because remember, the moon and the Earth are tidally locked, so we're always looking at the same side of the moon. The point on average that is directly facing Earth. And then the y-axis just completes the right-handed system. And so once again, that's going to have a very simple rotation between the moon-centered, moon-fixed frame and the moon-centered inertial frame. Same basic idea as the ECEF and the ECI frame. So this is that y'all are tracking. The moon-centered moon-fixed frame, or MCMF. Okay, so craters would be defined in the moon-centered moon-fixed frame, right? Or the Apollo 11 landing site would be defined in the moon-centered moon-fixed frame. Those things aren't going to move. At least they shouldn't move, right? There'd be a problem if the craters start moving. That would be like some Apollo 18 nonsense. But anyway, that's the idea there. So the moon-centered inertial frame would be nice for describing the orbit of a spacecraft around the moon. The moon-centered moon-fixed frame would be good for describing points on the lunar surface. Same thing as with the Earth. So you could also consider a frame it's the word frame fixed in the principal axis of a spacecraft body. Might call that the spacecraft body frame. And you could also consider a frame fixed with respect to an instrument, a camera, etc. So got a kind of little diagram here. Imagine you've got a spacecraft which consists of a cube. That's a cube with solar panels coming out the side. You might say that it's got some x-axis this way, and you might say that it's got some y-axis out the solar panel, and that it's however you like to, really. Or maybe you have a camera, and let's say that camera is like a triangular prism with some sort of a, like that's its little light baffle there. Then you might say that it's got some z-axis coming out the front. It's got maybe some x-axis coming down, something like this, right? That's the idea. So you can imagine a reference frame fixed in the spacecraft body, fixed in an instrument, fixed in the Earth, fixed in the moon. So then to list the frames we've discussed today, somebody shout them out. What have we heard so far?
The moon centered, moon fixed,
Yep.
Earth centered, Earth fixed,
Yep.
Earth there was like the moon centered inertial frame, the geocentric celestial reference frame,
Yep.
and there was like one more, the inertial or international celestial reference system.
Yep. These are the big ones that we're going to use in this class. So International Celestial Reference Frame, which is basically the sun frame. Earth-centered inertial frame, which is the Earth frame, but it doesn't rotate. The moon-centered inertial frame, which is the moon frame, but it doesn't rotate. The Earth-centered Earth-fixed frame, which is the Earth frame that rotates with the surface of the Earth. So the position of Greenwich, England in the Earth-centered Earth-fixed frame is constant, whereas it would be a little bit wonky to describe the orbit of a spacecraft in a rotating frame. That'd be a bit of a bummer. Moon-centered, moon-fixed frame, same relationship. And then there's the camera frame, which, because we're going to be doing a lot of camera-based navigation, if you take, for example, a star sighting using a star tracker, you're going to get a star body vector in a camera frame or in a star tracker frame. So it's necessary to think of those as well. And that's pretty much it. So I appreciate everybody for sticking around a few minutes later than I meant to. Those are my notes for the day. Y'all are dismissed, but if you want to stick around and you have any questions, let's do it.
I have a quick question about the homework.
Sure.
So are you,
homework 0?
yeah, are you really strict about like the length of the cover letter?
No,
Because mine was like a page and a quarter.
I would practice trying to get it down to a page. I'm not going to get angry at you, but I think that the effort that would go into editing it down would kind of trim it so that it's even more kind of, editing it makes it more sleek, if that makes sense. So
Okay.
I'm not going to get mad, but do your best to keep it down to a page if you can.
Okay.
Yeah,
Thank you.
absolutely. Any other questions, everybody? I know today was a little bit of boring laying the foundation stuff, but this is the ditch you got to dig so that later we can do some more fun stuff.
Thanks, Paul.
Absolutely. Have a good one, everybody.
Have a good night.
Yeah, take care. I'll see you next time. And we don't have class on Monday, do we? We got right?
Oh yeah, it's Martin Luther King Day.
That's right. So I'll see y'all on Thursday.
All right,
See you Thursday.
All right. Take it easy, everybody.
Thank you so much. Have a great night.
Of course.
Thank you.
Have a good night, Paul.
Yep. Take care.